Hi there, in this video we're going to do a practice problem with linear regression, and you're welcome to try this on your own first and then come back and double check. So let's get started. Here's a data set for Mustang cars that are for sale online. Okay, we have looked at the price variable by itself, so it was one of our simulations. I think it may have been either sampling distribution, I can't remember exactly which one it was, but we have looked at, we've seen this price variable, this price data set. It goes down further. But now we've got more of this data set. We have three variables. We have the age for each car, we have the mileage of each car in thousands, and then we have the price also in thousands. Okay, and this is great because now we can talk a little bit more about when there's a positive association versus a negative association. That's a hard word to say. Okay, so mileage versus age. Would this be, if we were to graph this, and we will, well, we'll graph some of it, but not all three at the same time. If we were to graph mileage and age, that in that case, mileage, age would be the X, and mileage would be the Y, or age would be the explanatory and mileage would be the response. Would that be a positive or negative association? Okay, so let's think about this. As age goes up, what generally happens to mileage? As age goes up, the mileage generally goes up too, right? The longer you have the car, the more you drive it. It can't go down. It could stay the same, but it can't go down. So this should be a positive relationship. Okay, and then I'll explain by saying as the age increases, mileage increases. Generally, right? Okay, what about price versus age? Okay, so then again, price would, age would be the explanatory and price would be the response because age is independent. So what happens as the age is going up of a car, what generally happens to the price? Generally goes down, right? So this is a negative relationship. Or association. So as the age goes up, price goes down. Now there are some cases, and I think Mustangs can be collectible, especially the really old ones, where if it's old enough, it goes up again, right? So maybe it's not even a linear relationship, but for most cars, if they're not collectible, for most cars, as the age goes up, the price goes down. And maybe at the very end of their life, they go back up again. Okay, now let's look at price versus mileage. Okay, this is interesting because age is definitely independent, right? The age of the car, you can't do anything to affect that. But then now, and we looked at two different Y values, but now if we look at miles and price, what do you think would happen there? Okay, so and which would be the explanatory and which would be the response? Would the miles affect the price or the price affect the miles? The miles would affect the price, right? So in this case, the mileage would be the explanatory and the price would be the response. So mileage is kind of in the middle because it can be either one depending on the context. Okay, so now what do you think as far as positive or negative? As the mileage goes up, what happens to a car? What happens to the car's price? As the mileage goes up, it generally has less life left, right? Less life left. So the price would go down. So as one goes up, the other goes down. So this is also a negative relationship. Okay. As mileage goes up, price goes down. And then in that case, sometimes age doesn't even matter as much as mileage, right? Like don't you look for a car with low mileage, even if it's older? So if you're looking in the market for a car, okay, it's been a while since I have. So, but my car's getting on the old side for sure. So might be looking pretty soon. Let's use Staplet to make a scatter plot of price versus age. Okay, we can only graph we're looking at two variables at a time. There is a multiple regression, and you may have seen that on Staplet, again, beyond the scope of this class, but you can look at many variables at the same time, and it's really interesting, okay, and determine which one affects it more. It's really, really cool. So take more stats, but we're not going to do multiple regression, so we're going to stick with two variables at a time here. So price and age. Okay, so it's the first one and the third one. So I'm going to go over there. It says we're going to do the correlation and if it looks linear, we always have to check that. It's kind of like a condition. So let me find my data. Here's my data. And age. I probably could have typed that faster than copying and pasting, but okay, so I'm going back to the Staplet homepage so I can just clear everything out. Here's multiple regression at the bottom, but we're not going to use that one in this class. So the explanatory is age, and the response is going to be price in thousands of dollars. Okay, so then I'm going to copy my whole age, just the age column. So this, if your data is in a spreadsheet, it works really well. Or if it's in my Open Math, that works really well. Okay, copy my prices over. Great, and then I'll hit begin analysis. Okay, so what do we have here? What does this look like? Does it look linear to you? Does it look, yeah, right now we only need to decide if it looks linear. It does look negative, right? And I purposely chose this because I wanted to look at a negative association because we had done two positive ones. It almost looks like it might be leveling off at the bottom. I mean, there's only so low a price can go, right? But let's scroll down. Let's see what it looks like with the line on it. So here's my correlation and here's the line. Yeah, see when you get the line, you're like, sure, it looks pretty linear. It looks like there may be an outlier, this one up here that was 7 years old, but 45,000. That seems like an outlier. Maybe that one had low mileage. You know, we could check that. So that one does seem to be off compared to the pattern. Okay, well let's keep going with this. So let's get our. Oh, by the way, you can also hide the dot plot and the residual plot if you don't want to see those, since we're not focusing very much on those in this class. So you can hide those if you want. Okay, here's our correlation. It is negative, which we expect because the line is going down. And then our correlation is moderate, like 0.7004. Okay, so I'm going to write that down before I go back to the notes page. Then our equation is y hat equals 30.2638 minus, so our slope is negative, that makes sense, negative 1.7168x. And then r is equal to negative 0.7004. Okay, if you remember, I haven't actually mentioned this yet. If you remember from algebra, a negative slope is one that goes down from left to right. And you could think of rise over run, you're going down. Versus our slopes have been positive in the last two examples because the line was going up. It was rising from left to right. So negative slope, negative correlation, negative relationship, those all go together. Okay, so here's what I wrote on the notes. I wrote the model. And then I wrote our correlation coefficient there. Okay, that's R. Okay, describe the association. So let's do it. The association between Mustang price and age is, okay, what do you want to put first? We could put negative, we could put linear. I'll say linear, negative, and moderate, with a correlation of negative 0.7004. Okay, and then I'm going to talk about any unusual features. So let's go back to the scatter plot for a second. I think I would probably just mention that one outlier. Sometimes outliers are easier to see in the residual plot as well. You can see that's the same point there, that 7-year-old, oh, actually, sorry, it was off the screen. This is the 7-year-old Mustang. And it does give you the value of the residual. That's really nice if we were using that. So I'm going to say the 7-year-old. Is there another 7-year-old? Let me go back to the notes. Here's a 7-year-old at 45,000. And it does have a lot of miles on it. It's got 33,000 miles. So I don't know. Maybe that one had some special, features, like leather seats or like some fancy upgrades or something like that. There's still always going to be individual to individual variation, right? Okay, so I'm going to say the 7-year-old. We don't really have any other identifier, so luckily there is only one. The 7-year-old Mustang may be an outlier. Okay. Great. Okay, a couple more questions. What does a positive residual mean in this model? Okay, so let's go back to the residual plot. What is a positive? Remember, positive means that our line is under. So all the dots above have positive residuals. So that means our model underestimates, right? That means our model underestimates the price for those cars. Okay. A positive residual means the model overestimates, under, just said under, underestimates the car prices or car price. Positive residual means the model underestimates the car price. Let's keep it singular. Okay, so remember these words kind of go opposite to each other. So the points above have a positive residual, but that means the model's below. So the model underestimates. And then let's see what the next question is. The next question says, what does the model predict for the price of a Mustang if the car is 7 years old? Okay, well, this is going to be interesting because this 7-year-old, it was the outlier, seemed to be an outlier, right? But we can calculate predictions. We have our model written up here. So I'm going to write that with putting in an x value of 7, okay? So y hat is 30.2638 minus 1.7168 times 7. And let's plug that in our calculator. 30.2638 minus 1.7168 times 7. That is 18.2462. Okay, I'm going to keep it all here because we need to interpret this. What does this mean? It's not $18, right? So we're making predictions. We need to go back to our units. And the price is in thousands of dollars. So for example, 32 means $32,000. I wish it was $32. 32,000. So where this decimal place is, this is actually 18,000s, right? So I'm going to say, I'm going to write this out. It's 18 comma 246. So I could stop there, or I could put 0.2 or 0.20, depending on how far you want to go out. $18,246.20. Of course, can we predict exactly to the cents? Probably not, but just interpreting from the number we get from our equation to our context is important. And I'm going to put the dollar sign there as well. So I could say the model predicts a price of $18,246.20 for a 7-year-old Mustang. Okay, and 7 is within our data set, right? So that's interpolation. 7 is well within our range of data values. It looks like we've got up to 15 or so. And if I looked back at the scatter plot, that could tell me as well. Looks like, yeah, so we've got 15 for 10,000. Okay, so for the 7-year-old car, we got 18,000, but this one was 45,000. So I have no idea how it could be that much more expensive. Maybe it was owned by somebody really famous or something like that. Okay, last question. Could we use this model to predict the price for a 25-year-old Mustang? Why or why not? Okay, so we were just talking about our X values going up to 15. And now we're trying to predict 10 years beyond that to 25. It's not a good idea, okay? So could we get a number? Yes. Should we? Probably not. So I'm going to say we could calculate it. But this would be extrapolation. Or this would be extrapolating beyond our X values. Okay, and now this might be a situation where it's getting to be collectible, right? So maybe this model doesn't hold for collectible cars. So we just don't know if it's going to apply or not. We could get, if we want to know about 25-year-old cars, let's get data about 25-year-old cars, right? And not try to use a different data set that doesn't apply, okay? So let's say there could be other factors. With older cars, like being collectible. Okay, so if we need to know about 25-year-old cars, let's get a different data set. We can look them up online, right? Okay, great. So I hope that gives you a lot of good examples for practice, and I'll see you in the next video.